So our first speaker in this session is Audrey Lustig, and not Nicola Toki, if you didn't hear the announcement this morning. And I just want to thank Audrey because she was just asked to do this talk sort of the end of last week, so she said yes and would come and fill the slot when Nicola couldn't make it. And Audrey is a postdoc working at the University of Canterbury Mathematics Department, and also working with Manaki Whenua staff, Roger Peck, who's in the audience, and Dean Anderson. And her topic is Lost in Space, Modelling Space Use and Dispersal of Mammals in Realistic Landscapes, which is a real challenge, but she's going to tell us about it. So join with me and welcome Audrey.
Hi everyone, thank you for being here. So one of the most fundamental piece of information that we need when we try to initiate any predator control or surveillance is trying to figure out where we can find our predator in the landscape, in which abundance and at which time. And we believe that modeling can help us answering those questions. So we understand that the distribution of our mammals are mainly constrained by habitats. And the habitat is acting in two ways on our species. In the first way is providing the resources that the animal will need to feed, to reproduce, to avoid competitors. And in mammals, it usually happens that the mammals will form a home range, a territory that is usually kind of exclusive from other species, from other mammals of the same species, sorry. And those home ranges are dynamic. Their size will change depending on their habitat. If you're in a really high quality habitat, they will have smaller home ranges. And if you're in a lower quality habitat, they will tend to need more space to find their resources. The other way habitat is influencing our predators is by affecting their movement, the way they move towards the landscape. It can either facilitate their movement or block them. This is not really relevant for predators in New Zealand because they seem to be able to move everywhere, but they show some preferences for some type of habitat, and we are trying to figure out which are those preferences. So one of the first steps you can do in modeling is trying to gather all the information you have. And the way we represent landscape as human is by having those land cover databases where we know everywhere which type of dominant habitat you have in the landscape. So that's what you can see on your left side. And to every category of land cover, you can try to match expected density of predators based on the literature and what has been reported elsewhere in New Zealand, and then projected to the Cap2 City area. So that's an example of what has been done here for possum density, where we know that in beech forests, those possum tend to occur at a density of 5 possum per hectare, for example. And will occur at a way lower density in grassland, for example. Based on that, if you zoom really deep into that, that's the way the landscape, I represent the landscape in my computer. So it's basically a raster cell where each square is simulating a different habitats. And those habitats can have carrying different abundance of predators. And then within each square, you can simulate the reproduction of your predators. So always taking the possum as an example, we know that those species can reproduce all the year round, but they seem to have a really high peak of reproduction in autumn and sometime in spring. So we can simulate the number of offspring that will appear in every raster cell at a monthly time step. The second step is trying to understand, once they're born, where do they move? So we know that in the case of possum and for other species, those little babies tend to stay with their mother at the beginning of their life, so we can associate their movement to the mother. But it comes to a point where they will need to move on from the territory of their mom and establish their own territory. And we know that this is controlled a bit by the local density of predators and the habitat quality. So if you have a very high quality habitat and not much predator around you, you're more likely to stay where you were born, around where you were born. However, if the habitat is full and you can't find resources anymore, you will need to move on in this landscape. So like this, you can move on towards your landscape, and we make sure that you don't move too far, because we know that the species after a certain point will just die after dispersal. So by integrating those simple rules in the model, what you can get is simulation like this one. So just be careful here with the scale. So I'm representing the density of possum over the capacity, where I started on the year 1 with a random distribution at a low density. And the maximum density you can have here is about 0.3 possum per hectare. And then I try to figure out where those possum will move in the landscape across the year, hoping that they will go through those high quality habitat, because it's what we observe in reality. So that's actually what we see after 15 years of simulation and running those models over many simulations. You can see that your possum will accumulate it in those beach forests or those high quality habitats. So it seems that we are able to reproduce patterns that we see outside. So that's already a good step, because it will mean that we could try to simulate the abundance of possum all around New Zealand or wherever you want. But what you can get also is like approximated or maximal number of species that you can expect in the area that you're looking at, because you can count the number that you get at the end of your simulation. This is without control, without competition. It's really the maximal number you could get. And probably very overestimating. Other information you can get is looking what happened with your newborns. So in red, I was trying to simulate, I have a few issues with my simulation here, but let's say I have 50% of my population that reproduce every year, and I try to see what will happen with those newborn over the year. So in yellow, you see those species that were born and could do their little dispersal and establish their home range. And at the beginning of the simulation, they seem to find the space to establish. And because we are in an uncontrolled landscape, over the year, this landscape tends to saturate. So this number of possum that can establish diminish over the year. In green is those number of little possum that were born and that did their dispersal but never found a space where to establish, and so they will die. And in blue is just those little possum who went out of the area. So a very interesting pattern you see here is that as you get to the saturation of your landscape, you see that actually most of your newborn will die, and it's something that we observe in reality. And it's something of high concern when you start to do control, especially if you do control before the reproduction period, where you're lowering your local carrying capacity, and so you're giving more space to your newborn to actually establish in the places where you trap. We can also look at different dispersal patterns just to see if we are actually matching reality and what we see. So on the left side, you see just the number of kilometers that your possum will walk, and on the right side is the distance in between where it was born and where it established its home ranges. So we see this nice Gaussian distribution with a peak about 2 kilometers. So we know that's also something we see in reality, where species tend to move a bit further from the home territory of their mother, but not too far. It's just a way of really checking what we see in reality and see if we could use the model to actually predict in new area what we observe. Something that I found the most interesting and that I think will be extremely relevant for trapping, especially when it comes to trapping and relying on landholder, is trying to see not only where species are important, but where they move and how they move from one property to another one. So on the left side, it's still is population density, and on the right side, I was trying to simulate the movement in between properties. So each dot is actually the centroid of your property, and if you see a line in between those centroids, it means that there was a movement in between two property, and the whites of this line represent the number of predator that moves in between those properties. So you can see a really high activity on the north of the area where you have high habitat, and we can actually try to quantify and give a probability of how many individuals we've moved from one property to another one. And I think this will lead to us the rest of the project. So where we are going on is then to bring some trapping on this model and try to see what will happen if some landholder will participate in the control and some will not, because we know that if some don't participate in control, they act as a source of predator for the neighbor, and so tend to discourage the neighbor to participate in the predator control. So by using that, we have a better information on where those wrong effects could occur. So some of the next research questions that we're going to try to tackle will be, can we identify those hotspots for different species? And are they matching with the trapping line that have been proposed, or can we propose the new trapping line that would be more optimized? Can we identify those corridors of movement in between property for any predators, and does it match what we observe in nature? And this is to actually try to control the reinvasion after you've done a control program. Once we get to the social component of the model, information or question we'd like to tackle will be either minimum participation of landholder that you will need to actually succeed in controlling at low density or eradicating your predator on the landscape scale, and can we identify key players and key location using this model? And that's it for me. Thank you.
Kia ora tātou. Mike, can you just put up your last slide again?
Yes. This one? Oh, the question.
Your research questions?
Sorry.
So coming from a practitioner point of view,
yeah.
I mean, we all probably already know that, yes, there are definitely sites where there's maximum probability of presence of predators. We already know that there's putative corridors that facilitate the ability of predators to move across the landscape. So I'm just wondering what's going to be new about what you're trying to look for?
I think we know that those different elements at the local scale, but we have at regional scale and under control, we have no idea if those corridors will be maintained. So will your trapping actually match those putative corridors or not? And will your people trap in those putative corridors? And if they don't trap, will you still be able to stop a reinvasion? So I think it will be more looking at larger scale. We have a notion of what happened at local scale and on the scale of the Cap to City. But when you move on at the full North Island, I don't think we have an idea what could happen. Does he answer your question?
Well, it'll be interesting to see. Thank you.
Yeah.
Can I'll just add a wee bit. I mean, if I can just add a wee bit to that, most of the modelling that we do now, we have a possum spatial model, and all the sort of parameter values are based on forest areas. We don't have good ways of modelling possum movement across farm landscapes and patchy habitats. So I think what Audrey's trying to do is contribute to our better understanding of what possums and maybe other species in the future, how they move across sort of patchy landscapes, which is sort of seriously lacking at this stage. Yeah. So I'm going to ask her a question. So in the last talk in the other session, Andrew Gormley put up some models for doing simulations and prediction, and then he put it out to the audience that we now need to collect the data to test the models. And I'm just wondering what sort of data do we need to collect to sort of test your predictions from your model?
So I think we have, we are working together with Andrew, so we are based on using his model as well. And the main thing we are struggling with is the probability of trappability, particularly during the dispersal phases. So we have information when we are looking at home ranges, but we have no idea how trappable are species when they move throughout the landscape. Yeah. Thank you.
Yep, one last question.
Your modelling was based on
Hang on.
juvenile dispersal. How would it change looking at males seeking out females in that landscape? Would they use because it's not then habitat driven, it's reproduction driven. So would that alter the matrix of the model?
I will definitely alter the matrix of the model. So the idea behind the model is that once you establish you're in a home range and that all those movements will be within that home range, so we are not getting into this level of details for mammals because we usually don't have the data to get to this level, and it will be too computer intensive to run it at way larger scale as well. So it's more an aggregate movement of adults.
Thanks, Audrey. Please join with me. Thank you.